Okay, so here's the title from our last lesson. It was compound interest. And I was telling the class that one thing you'll need to know is that in this lesson, you will see a number E pop up quite a bit. And for now, let me just tell you that E is a number, and that is its approximated value. So your pre-calc and calculus teachers will tell you what E is, where it comes from, what it represents. We can spend a whole day talking about this, but let me just tell you here now that E is a number, not a variable, and that is its approximated value. So jot these down, would you now? These are the compound interest formulas that we will be using for this lesson. And you can pause the video if I ever go too fast, but let me just tell you what these things represent. So T is time in years, R is the interest rate, P is the principal, it's what you deposit on day number one. You see, the idea for these problems is you invest some sort of money and it either grows or decays over time. Or you have some sort of valuable possession and this item, it grows in value or decreases in value over time. And it's up to us to know which of the two formulas to use. And so that's what T, R, and P represent. A is sort of the final or the current value of your money or your bank account or whatever item you possess. So we want 1 penny to become $1 million. It's gonna take some time probably, and that's the goal. A penny to $1 million in an account that compounds monthly with this percent interest. So the goal is how long? Now, the first thing we have to decide is which formula to use. Are we gonna use this formula or are we gonna use this formula? Now, here's how you can make that decision. Looking at the word problem. If the word problem says the word continuous, then we use the continuous model. If the word problem does not mention the word continuous, then we use this model up here. So for sure, for this first exercise, we are gonna use that upper model up there. So why don't you write that down on your notes with me? And then maybe what we can do, what we did in class, which is we identify what everything represents. So let's see. So P is the principal. It's what you deposit day number one. In this case, we have 1 penny, which as a dollar is 0.01. R, 1 is just 1, it's just part of the formula. R is the interest rate, which they say 27%, which of course is 0.27. I'll let you know what K is in just a moment. T is time. Time is how long it takes for a penny to turn into $1 million. We don't know, that's the goal. We were trying to find time, that's the goal. But we do know that the final amount, A, is gonna be $1 million. So P is the initial, R is the interest rate, T is time, A is the final amount. Now K. K is the number of compounds per year. Compounding is when your money sort of grows and grows and grows and grows and grows and grows. So for this model, K is a number and it represents how many times your cash money is compounded in a 1 year span. Here, they're saying that your money gets compounded every month, but we're talking about 1 year. So in 1 year, how many months are there? 12. And that's how you decide what K is. It's the number of compounds within a 1 year span, in this case monthly, so 12. If they had said daily, then that would have been like 365. If this said like weekly, then that would have been 52 and so on and so forth. So now let's rewrite this problem with all the numbers plugged in. And so we're trying to solve for T, so maybe we can divide the 0.01 into both sides. And if you look in the parentheses, that's actually just the number. And so we can actually just type that number in. And then maybe I can switch left and right. And now because our exponent has a variable, we're gonna write this into logarithmic form. And then to isolate T, time, we can divide both sides by 12. And so if you round to the nearest whole year, we have about 69 years. So it's gonna take quite a minute for your penny to become $1 million in an account that does what is being described here. So that's gonna take quite a bit of time. Let's try one more problem. And how about we try this one here? So maybe you guys can copy this one down. And now the first thing is we have to decide which of the two models are we going to use. this one or this one. There's like a million other formulas we could play with, but for the sake of time, we're just gonna focus our attention on these two models. So is it that one or that one? Well, the key word here is that the shoes are appreciating in value continuously. So that leads me to believe that I should use this model right here. And maybe we could label what everything represents. So let's see, the principal amount is the value of the shoes in 1985. They were just $65. We know that E is about 2.71, which is what we discussed a moment ago. R is the interest rate. That's actually the goal, so we'll just call that goal. T is time. We're going from this year to this year. So how many years have elapsed from there to there? About 36, yes, about 36 years. And the final amount is 2,000. So the shoes have grown in value as time has gone by. So let's write down this model with all the things plugged in. We're trying to find R, so maybe we can divide 65 into 2,000. So I divided 65 into that, and I did round this number. That's totally fine. You can round a lot in this little section. Answers will be accepted as long as they're close to the real answer or to the exact answer. And that's just there. You don't need the parentheses. R times 36 is 36R. We can switch left with right. And then, as we did before, we can write this into logarithmic form. And then we can divide both sides by 36. And the decimal just keeps on going. So they wanted to know the growth rate. So that's the decimal, but it is customary to turn this into a percentage. So we move the decimal 2 spots to the right. Anything close to that will be totally fine. So that's how some of these problems can work out. There is a video uploaded onto YouTube that has some of the homework problems worked out. So give that a go if you'd like.